In this video, we cover risk and uncertainty in the context of portfolios of investments, either investments like stocks and bonds or investments for a company in projects. The first thing that we want to talk about is expectations. So the expected value operator is additive and linear. Now that means a couple of things. One of them is that the expectation of something you know for sure, like the risk-free rate, is just that thing, the risk-free rate. Second, if you combine things in portfolios, for example, suppose you have $100 and you put $50 into, say, Jefferson Jingles. You take the fraction that you put in that first investment times the expected return on that investment plus the fractions that you put in every other investment times the expected returns in those other investments and add them up, you get the expected return on the portfolio overall. So for example, if you had Roosevelt routers and Jefferson Jingles and were investing in a portfolio, half of your money in each, what you would do is say half my money is in Roosevelt routers at an expected return of 5%. The other half of my money is invested in Jefferson Jingles at an expected return of 7.5%. The weighted average expected return that holds overall in your portfolio is just 50% times 5% plus, in parentheses, the other half of the money, 50%, times 7.5. 6.25% overall. If you were to change the weights and a third of your money was in Roosevelt routers and 2/3 in Jefferson Jingles, this would push the average closer to Jefferson Jingles. Because 2/3 of the weight is on Jefferson Jingles return. So a third times, nope, that didn't work. A third times 5% plus, in parentheses, 2/3, 7.5%. Oops, it didn't do that one right, did I? A third at 5% plus 2/3 at 7.5% is 6.67%. Now again, in this formula, we're adding. The difference between this and probabilities determining expected return on an individual asset is 2. First of all, we're putting investment weights, not probabilities, in here. We're multiplying not by returns that we see for each outcome, but the expected return for each different asset in our portfolio. Now, variance or standard deviation don't work this easily. Now, the variance of something you know for sure is 0. So the variance of the risk-free rate is 0. But variance for a portfolio is not the weighted average of the two individual variances, nor is standard deviation the weighted average of the two individual standard deviations. And the reason is that depending upon the correlation between two investments, the returns may tend to reinforce each other, or they may tend to cancel each other out. So there are 3 components to risk if you have a 2-investment portfolio. One of them is an individual contribution to risk from the first investment. That is in proportion to the investment weight squared and the risk of that investment measured by its variance. There is also a contribution to risk coming from the other investment in proportion to its weight squared and its variance. In addition to the individual contributions to risk, there's what we call a diversification term in here. The diversification term reflects the tendency for the two investments to move in the same direction at the same time through the correlation, the relative size of typical moves through the two standard deviations, and the amount you have invested. Now, for every combination of two investments, there are two of these diversification terms representing one stock going up while the other is going down, canceling each other out, and the opposite direction, the first stock going down and the second one going up. To get the standard deviation, you would take the square root of that whole thing, and then you would be back in return space instead of return space squared. Now, as long as the correlation term is less than 1, this actually reduces risk, because if the correlation is less than 1, there are at least some times when one stock is moving up, the other is going down, and they cancel the risk in those cases. We call that the benefit of diversification. So, for example, with Roosevelt Routers and Jefferson Jingles, if we have half of our money in each of the two investments, you would compute the variance according to the formula where there's one term for each of the two investments and two diversification terms. Actually, in order to make that simple, what I'm going to do is I'm going to put that formula in what I'm going to call a box. Okay, and the reason is that each element in this box contains the same portion of the formula. So I'm going to label the column Jefferson Jingles and Roosevelt Routers. The rows Jefferson Jingles and Roosevelt Routers. Then what I'm going to put in each one of these boxes is the investment weight in the investment in the row and the investment in the column. So the weight in the row here is a half. The weight in the column is a half. Here the weight in the row is a half. The weight in the column is a half. The weight in the row is a half. The weight in the column is a half. The weight in the row is a half. The weight in the column is a half. Then you put the standard deviation of the column and the row investments in each square. Here the standard deviation of Jefferson Jingles is 707. That's the row, the column, and then the rows. Make the decimal point a little smaller there. The columns for Roosevelt Routers. Roosevelt Routers, remember, had a standard deviation of 0.1436. This is the column, and this is the row. Finally, in each one of the cells you put the correlation between the row and the column investments in. An individual stock's or investment's correlation with itself is always 1. And the correlation between Roosevelt Routers and Jefferson Jingles, if you recall, was 0.492. Roosevelt Routers and Jefferson Jingles are in the row and column in the upper right corner, and the row and column in the lower left corner. What you do is you multiply inside each of these boxes first, you add them up, and you have the variance. I'll show you how to do that on the calculator here. Now what I've done is I've already calculated, in the last video, the standard deviation of Jefferson Jingles, 707. Roosevelt Routers, 1436, and the correlation, 492. I'm just going to use those to do this calculation here. So in the upper left corner, half of my money is in Roosevelt Routers times half of my money in Jefferson Jingles, Jefferson Jingles in both cases, times the standard deviation of Jefferson Jingles, I'm sorry, that's Roosevelt routers in the upper left, times Roosevelt routers. I'm going to store that to have it for later. Now I should go back here because I have these labeled wrong. This should be Roosevelt routers and Jefferson Jingles. Going back to the calculator, I've calculated the upper left corner. Now what I'll do is the upper right corner, half my money in Roosevelt routers, half my money in Jefferson Jingles, Jefferson Jingles standard deviation, Roosevelt routers standard deviation, correlation. I'll store that. I'll also store it in another memory register because it's the same calculation in the lower left corner. In the lower right corner, it's Jefferson Jingles, Jefferson Jingles, Jefferson Jingles, and Jefferson Jingles. Now I just need to add up these four things, adding them up. And I'll take that's 0.008906. Taking the square root of this gives me the standard deviation. Square root. That's 9.44%. Now note, that is less than the weighted average of the individual standard deviations. Because the weighted average is a half times Roosevelt routers, plus in parentheses, a half times Jefferson Jingles, 10.072. So this standard deviation reflects a reduction in risk relative to the simple average of the two individual investments' risk. This is the benefit of diversification when you invest in more than one investment. There are no benefits if the standard deviation, if the correlation is 1. If I were to plot out the standard deviation on the bottom axis and the expected return on the left-hand axis of a portfolio where the correlation is 1, I would just get a straight line connecting the two investments. What we call the efficient frontier is the highest return you can get for the risk, the lowest risk for the return, or both. The entire line is efficient. As the correlation drops below 1, you begin to get some diversification. If you go to a correlation of 0, you get this bow-out effect here, where relative to the straight line connecting the two investments, you get lower risk for the same return, higher return for the same risk, or both. The efficient frontier is everything up and to the left. Actually, the min point here is the beginning of the efficient frontier, and everything with a higher return for the risk, a lower risk for the return, along this line is called the efficient frontier. If the correlation drops all the way to -1, you can actually balance out the portfolio holdings so you reduce risk to 0. Then anything along this line is the efficient frontier. you would never hold anything in here because you can increase the return while decreasing the risk moving up and to the left. So depending upon how correlated the investments are, you can get moderate to a great deal of diversification reducing risk by holding more than one investment. If you have a large portfolio, you have individual contributions to risk for every individual investment, and you have diversification terms. If I compute the standard deviation according to a box method, which I'll show you in a second, these are called the off-diagonal or diversification elements. Now notice these depend upon the investment weights and the tendency for the stocks to move together at the same time, the correlation, or when you multiply by the two standard deviations, the covariance. The way that we'll do this is we'll calculate these things according to a box method. For every investment, and you can see how this will work very easily in Excel, making a big table, you put into the cell the weight of the investment in the row, weight of the investment in the column, standard deviation of row, standard deviation of column correlation. Now this will always be 1 down the diagonal. The diagonal then gives you the individual contributions to risk of each of the individual investments automatically as you calculate through the table. Then what you do is for every row where you have an investment, you put the investment weight in all the way along that row. And for every column that you have an investment in, you put in the investment weight all the way down the column. You do the same thing with the row standard deviations and column standard deviations. And then you put the correlation of the row and column in, each one of the items. Then what happens is every one of these gives you 2 diversification terms, which is the number you need, for every combination of 2 investments. That depends upon the investment weights and the covariance of the 2. You multiply inside the table like we just did, you add them up, you have the variance to the entire portfolio. If you want to get the standard deviation, you take the square root. So what we'll do is we'll do that. This is the set of diagonal terms. These are the off-diagonal terms. And what I'm going to do is show you a pretty simple little exercise here. What I'm going to put in for an investment weight is called the naive portfolio. If you have 10 stocks, you put a tenth in every one of the investments. If you have 250, you put 250 in. So then you just do a little algebra here. You split out one of the weights. You split out some combination of the weights here. You add these things up, you average across things, and what you get is the following result. The variance of the portfolio is 1 over the number of investments that you have times the average variance of the individual stocks. Now this number goes to 0. This number, it's 1 minus the number of investments you have over the number of investments you have times the average covariance. That goes to 1. So in the end, and the only really important thing to remember here, is that as you add stocks to your portfolio, the risk of the portfolio is determined entirely by the average covariances of investments within the portfolio. Or if you look at this table, it becomes fairly obvious. If you have a fairly large portfolio, say the S&P 500 with 500 stocks in here, what happens is these terms down the diagonal, there's 500 of those. Multiply 500 by 500, there's 250,000 terms. So 249,500, by far and away the dominating portion of this, is in these terms that give covariances across the investments. What that means is the driving force behind risk in a portfolio quickly becomes the covariance, the tendency of all of the stocks to move together at the same time. And you can see this fairly quickly here. What I've charted out here is the variance and covariance of a portfolio, the variance of a portfolio that has a variance of 25% and a covariance of 10, a variance of 25% and a covariance of 0. And you can see very, very quickly that the variance of the portfolio drops to 10% and 0% as I add investments. By the time I get out here to 20, 30 stocks or so, the diversification effects of the investments in the portfolio are dominating, and it's the average tendency to move together, reflected by the covariance, that determines the risk in the portfolio. This was what will determine the risk for any well-diversified investor, and forms the basis of what in the next video will become the capital asset pricing model, or CAPM.